This is Alicia Carriquiri welcoming you to our first webinar of 2019. Today's speaker is our very own Danica Oman, and she'll talk about weight of evidence and strength of evidence in two chapters. Today is chapter 1. Stay tuned for chapter 2 on February 4, same day, same Monday at the same time, I believe. Always visit our website, forensicstats.org. We have a lot of announcements and much good material for you. So without further ado, here's Danica.
Thanks. Thank you for joining, everybody. So today, if I can get this thing to work.
No, you can use the keyboard.
Hit the mouse to make sure that
Here we go. All right, so today, like Alicia said, we're going to cover some basic topics about weight of evidence. So we're going to start out with just a quick introduction, some basic ideas about what the weight of evidence is, and then talk about kind of this timeline of events that I thought was kind of fun and interesting that led up to how we got to where we are today, talking about the weight of evidence. And so that will hopefully bring us around to the conclusion of part 1, and then for part 2, we'll talk about some additional topics in February. So kind of to get started, interpreting forensic evidence is something that requires sort of a big collaboration. So it's not just statisticians, but it's also all types of different scientific practitioners, legal professionals, and then even laypersons, people that are interested, people like jurors. And so it's really a big collaboration. And this is one giant wall of text, but it's kind of this nice quote that I found from this famed criminalist, Paul Kirk. And what it basically says is that we all need each other. So criminalists need statisticians, statisticians need criminalists. Without the other one, we're each only going to do a mediocre job. So the statisticians need criminalists to talk about what types of problems and explain them to the statisticians so that we can really be effective in what we're doing, because the area of forensics is really quite different than a lot of the other problems that we encounter in statistics. So without some sort of additional instruction from criminalists, we're not going to be able to offer much useful assistance, as Paul Kirk says. And then the criminalists need the statisticians so that we can actually give some meaningful analysis and actually talk about what the interpretations mean for forensic science. So we each need the other one, and I think that's really an important thing, and something that we at CSAFE are really trying to do is bring everybody together so that we can do one really good job instead of 2 mediocre half jobs. So I'm going to start with some things by I.J. Good, since he's the one in 1950s-ish that talked about what the value of evidence really was. So he talked about the value of evidence in this really general framework, and he talked about it as being the Bayes factor. We'll talk a little bit more about what this is. But then he also defined the weight of evidence as the logarithm of the Bayes factor and nothing else. And he later goes on to say that we really need to have the same sort of terminology for everybody. It's not a useful terminology if it's only being used by statisticians. And so being the really, important guy that I.J. Good was, everybody hopped on board. And so now we call the Bayes factor in forensics the value of evidence. So this is essentially, in a nutshell, what the Bayes factor is. So it's that ratio in the middle of the 2 probabilities. So really, to define the Bayes factor, we need a couple of different pieces. We have to have a probability operator. And in I.J. Good's world, this probability operation was a subjective Bayesian probability. So it was personal to the person who was actually performing these computations. We have to have some evidence, so we denote that with a little e, and that's going to be the data that you're going to use to update your odds. And then we have these things, they're denoted by H's, which was typically for hypotheses. Most people have been moving now towards calling them more propositions to kind of distinguish between the fact that we're not doing like a traditional frequentist hypothesis test, but instead we're doing this sort of Bayesian decision framework. And so they like to use propositions to distinguish the two. Sometimes we also call them models to talk about maybe doing a Bayesian model selection, again, to distinguish from the fact that we are not doing hypothesis testing. And then there's this last piece that's often omitted from all the notation, and this is going to be the background information. And it's typically omitted because it stays constant throughout this entire process. It's not changing. And so that's typically why it's omitted, not because it isn't important, but just because it's fixed throughout the entire thing. So like I said, that middle ratio there is called the Bayes factor. And so that is the value of evidence in forensic science. Now, if we want to talk about the weight of evidence, what we would do is we would take the log of that ratio. So instead of having this division, it would turn into a subtraction. So that's often a lot easier for some people to think of the weights as being sort of this additive or this subtraction, as opposed to thinking of more of like a multiplication or a division. It seems a lot more intuitive to some people to think about the weight as opposed to the value of evidence. So they would use logs. So while this form seems like a very simple thing, you find your Bayes factor, you multiply it by your prior odds. So this is what you believe about your two different propositions before you've observed any evidence. And then you arrive at what you're actually interested in, is your posterior odds after you've observed your evidence of the two different hypotheses. So like I said, while this looks very simple, there are very many intricate pieces within each one of these different things I've listed here that can often cause problems. And we'll talk about a little bit more of the details of each one of these pieces coming up. So once you have this thing, like I said, you multiply it by your prior odds to get your posterior odds. And if we're talking about the value of evidence or the Bayes factor, if you have a Bayes factor that's greater than 1, then that means that you increase your odds. If it's equal to 1, your odds are unchanged. If it's less than 1, then it decreases the odds. So this is like saying that a Bayes factor greater than 1 indicates support for HP or the prosecution proposition. 1 means that the evidence is neutral. It doesn't indicate one proposition over the other. And less than 1 means that it supports the defense proposition. So these are sort of the typical things that we think of when we are interpreting the value of evidence. But a lot of times this is, again, kind of difficult for people to think of in terms of value of evidence, because the range for the Bayes factor goes from 0 to infinity with a cutoff point of 1. So you have this really non-symmetric range, which is often hard for people to conceptualize. So if you think about the weight of evidence, so the log of the Bayes factor instead of the value of evidence, you get this more symmetric range where you go from negative infinity to infinity and you have a cutoff of 0. So it's much easier to think about kind of what those numbers mean for some people, because they're maybe a little bit more directly related, while other people prefer the value of evidence. So that's why we have both value and weight. So another way that we can think of interpreting the value of evidence in a little bit more detail is if you have a value of evidence greater than 1, then you would say it's X times more likely to observe the evidence if HP is true than if HD is true, where you would plug in the value of whatever the Bayes factor there is for the X. If your value of evidence is less than 1, then you would plug in 1 over the Bayes factor and say it's more likely to observe the evidence if HD is true than if HP is true. So sort of very simple ways of how you could use the quantitative value of evidence to interpret what that means. And of course, this interpretation depends very much on what you pick for your propositions, which we'll talk more about. Another way that you can sort of talk about what the value of evidence means in your case is to use these different verbal scales. Maybe the quantitative value of the evidence is difficult for you to conceptualize. You can plug it into one of these bins. And this particular verbal scale is one that I have gotten from the European Network of Forensic Science Institutes guideline. And so this is something that they use throughout that network when they're reporting on the values of, here they say likelihood ratios, they really mean Bayes factors. And so you can see the different things that they have, but mostly they're talking about whether or not you have support for one proposition over another proposition. And they use words like weak or moderate or, you know, strong sort of support or extremely strong support. And, you know, it basically bins up your different likelihood ratios into maybe values that you can understand a little bit more. Now, it's been shown by some people that not everybody interprets these verbal words that they give back to these particular values for the Bayes factor. So what one person might think of as moderately strong support may not correspond to a value that somebody else might think of for moderately strong support. So these have not quite been adopted for use in the US court systems yet. This is something that they're doing in Europe a lot. So now, like I said, we're going to talk about some more of the details into how we actually go about finding this value of evidence. So in order to actually quantify what the value of evidence is, you have to have some well thought out propositions, or those hypotheses, HP and HD. You have to have a clear definition of what your evidence is. So what data are you actually going to use? And then you have to specify the appropriate background information. So this is something that I think is often very difficult to do without some information from a criminalist to figure out what information you should be using and what information you should be calling evidence. So to start off with, we have a variety of different levels that we can use when we're talking about hypotheses. So sort of starting from the most serious level down to less serious, we have offense, activity, source, and then subsource level. So here I've cited Kwan, that's that number 5. This was a dissertation out of UC Berkeley, but there's also a very nice paper by Cook and his colleagues as well, talking about the hierarchy of propositions. So just to give a brief example here, let's imagine that there is this lady, Mrs. X, and let's say that she is accused of murdering her husband, and they have retrieved the bullet from his body and they've analyzed it, and this is the evidence they have to use against Mrs. X in the murder of her husband. So at the offense level, that proposition would be concerned with whether or not Mrs. X is actually guilty of murdering her husband. And then at the next lower level down, at the activity level, it could be something like Mrs. X fired the weapon. Okay, so maybe it wasn't actually murder, so it was maybe a less serious thing. Maybe she fired the weapon in self-defense. As far as source level, it could be something like whether or not Mrs. X owns a gun that could have fired the bullet that killed her husband. So she may have owned the gun, but maybe she says that she's not the one that actually fired it. So she would not then be, guilty of murder at that level. So actually having the gun is less serious than firing it. And then finally at the subsource level, it could basically say that Mrs. X's gun is the gun that fired the fatal bullet. So these are kind of the different levels of hypotheses that we could be concerned with. So typically, the court is interested most often in offense or activity level, but what the practitioners or the witnesses provide is typically something at source or subsource level. Okay, so after we have our hypotheses, the next thing that we need to do is figure out what type of evidence we're going to use. And often what's considered evidence is going to depend on what type of hypotheses that you are considering, what level are you looking at. as well as, various other additional circumstances that might tell you what evidence you could be looking at. So we can break down what evidence looks like into sort of the physical object and then the measurements on that object. So the physical object might be something that has an unknown source, like glass fragments that you could find on a suspect's shirt, somebody who is suspected of breaking into a house. And then the known source could be the glass fragments that you find at the crime scene, for example. So the actual physical objects there would be the glass fragments themselves. You also use words like crime scene or laboratory samples. So a crime scene could be something like a footprint that you find at the scene of a crime and you take a cast of it. And then the laboratory sample would be you find the suspect's shoe and then you make a print of that shoe. So it could be something like that. We might also use words like recovered versus control samples. So something recovered from a crime scene might be like a latent print that you find. And then the control would be you find a suspect and then you take, their rolled prints of each of their 10 fingers on a card. So that basically talks about the different types of physical objects that we can look at. I prefer to use the term unknown source and known source since I think it's the most general and encompasses all sorts of things. Or if you were use things like crime scene versus laboratory samples or something like that, oftentimes the roles of what is a known source and unknown source could be reversed, like in the case of glass. So I prefer unknown source and known source for our objects here. And then it's often highly debated what type of databases we should use and whether or not these databases should actually be included in the evidence itself, or if the database should be included into some sort of background information, that I part of the Bayes factor. So the way that I typically like to do it is to think of the database itself as being part of the evidence. But actually defining what this database is of course something that's very much open to research and discussion lately. Okay, so now that we've talked about the physical objects, what you might actually be modeling with our statistical models or our statistical analyses may not be the actual physical objects themselves, but maybe some measurements or some discussion of the features of the objects. So the features can have a couple of different characteristics. They could be class characteristics, or they could be subclass, or what's sometimes called individualizing characteristics. So these class characteristics could be like the type of gun, maybe it's a Ruger, or the caliber of the bullet, where the subclass characteristics are the markings on the bullets that have been caused by the rifling of the barrel, for example. We also can have categorical measurements or features, such as when you're looking at fingerprints, you can have a loop or an arch or a whorl type of fingerprint. So that would be a categorical feature. We also have quantitative features, things that are continuous. This could be something like the trace elemental composition of glass, or something that's discrete, maybe like the number of short tandem repeats at a particular loci when you're looking at DNA. Another very important thing that we need to look at when we're thinking about our evidence is how many dimensions we have, because a lot of times that will really indicate the type of statistical analyses that are available to us. So if you have a really high dimensional feature space, it might be very difficult to statistically model and come up with likelihoods for that type of evidence. So the number of dimensions here is something that's going to play a very important role. So I've sort of talked here about physical objects. That's not the only type of evidence you can have. You can have evidence in sort of non-physical form too, like, maybe somebody said something that gave them motive, and then somebody came in as a witness and said, oh, this is what this person said. That's not something physical that you can touch or measure, but that could be considered evidence too. This is very difficult to sort of conceptualize for me, so I guess I focused on the physical objects here, but that's not the only type of evidence. Okay, so we talked about hypotheses or propositions. We talked about evidence. Now we need to look at this last piece, that I piece, the background information. It's a really important piece that I think is often overlooked. I know that I am guilty of this, as well as I think very many other people. You sort of delete it from the notation and then out of sight, out of mind. But I read this kind of interesting paper that I think helps kind of focus your thoughts about what is information is evidence and what information is background information that you should be including or thinking about when you're actually deciding what your propositions are. So this is something that I am in no way an expert on, but what I can gather from this paper that it's very case dependent. And then something that I sort of thought of while I was reading through this is determining now about some of the things we know about bias, how much of this relevant background information could be biasing to you and at what various levels or times in this investigation or court case would you want to reveal that information. So while the background information may be relevant, I wonder whether or not we might be biased by using some of that. So just kind of food for thought there. So I think now that we've touched on all of the pieces that we need when trying to quantify the value of evidence is the word I'm looking for there. And now I would like to kind of briefly talk about sort of this interesting timeline of events that, well, I thought was interesting for how we got to where we are now, thinking about the value of evidence as the Bayes factor. So I have cited this paper that talks about really early versions of statistical thinking and Bayesian reasoning and forensics that go way back to the late 19th century. And so this particular paper that I'm citing here seems to focus sort of on things that have happened by Frenchmen. So I think it would be very interesting to hopefully find some sort of similar history for non-French people, but it gives us really cool Sherlock Holmesy type account of some of the things that led up to this Bayesian thinking in forensics. So this first guy here, he was a French police officer, and his problem was identifying habitual offenders. So somebody gets arrested on their second offense and they want to know whether or not it's the guy that, committed the crime last week, and they didn't really have very good record keeping. So what they did is they measured various parts of the body and sort of kept a record of these measurements. So for instance, they measured the length of their finger and their arm and their legs and things like that. And then they had sort of this range of uncertainty. So if it was inside the range, it could be the same guy, or maybe it was somebody else. And so there's sort of some interesting cases here that you can look at. A couple of interesting cases were the Howland Will case. This was a US case where they were trying to determine whether or not a signature on a will was forged, or the very famous Dreyfus case in France where I think this was a French captain who was accused of treason, and he had supposedly written some notes to German intelligence or something like that, and so they were using the handwriting to determine whether or not this guy was actually accused of treason or committed treason. So these were two very interesting cases where they had used some sort of probabilistic interpretations of handwriting to come up with their ultimate decisions in this. And then I also find the very last example interesting. So this was a French professor of forensic medicine. He had done some work, I think, with human hair and firearms and bullets, and also for fingerprints. So even back to the late 19th century, this guy was interested in the probability of finding and coincidentally corresponding minutiae for fingerprints. So this just tells us how far back some of these things go, like handwriting and fingerprint evidence and so forth. So an interesting read, if you want another account of this, there's also a nice historical background chapter in a book by Aitken and Taroni that I think is good too. So before we actually started working on things in sort of this traditional Bayesian decision framework, we tried out a couple of other things as well. So this gentleman, Kingston, he was a student of Paul Kirk's at UC Berkeley, and he developed some nice methods for identification and individualization of transfer evidence. But this is something that we are moving away from because it implies higher levels of certainty in testimony and reports and things than we would typically like to see now. So I'm not going to focus much on that. But then there's this guy, Parker, and he developed a two-stage approach, which was a very cool approach that I think remains popular today, kind of across forensic evidence interpretation in the US. And then it applies to this very nice problem involving glass evidence that's very close to my heart that I keep going back to. And so this two-stage approach, as the name implies, has two stages. So the first stage is kind of this exclusionary stage. So you do some sort of test and you figure out how atypical or how unlikely the evidence would be if it was generated under your prosecution proposition. So what you're trying to figure out is whether or not, for example, the suspect can be excluded as the source of some sort of trace, or whether or not two different traces, maybe from two different crime scenes, can be excluded as having come from the same source. And so this uses sort of traditional ideas of kind of frequentist hypothesis testing and things like p-values. So you're looking at tail probabilities, or you're looking at using distribution functions for this. And one sort of example of where this is being used today is in the ASTM standard for trace elemental composition of glass. It gives a very nice approach for how to basically do the first stage of this two-stage approach. However, that does not talk very explicitly about how you would do the second stage. And in fact, the second stage is something that I think is still sort of up for debate today, and people are talking about how we should do this second stage on rarity. So if you have found that a suspect cannot be excluded, well then how many other people could you exclude, or how rare would it be to just randomly find somebody who you could also not exclude? And so I think part of the reason why this has been up for debate is because this stage really relies on having a defined alternative source population, or what we call a relevant background population, something like that. And so really what you're trying to do is find some sort of random match probability using the population or this database suggested by the defense proposition. And so it's debated whether or not you should use just sort of a general random match probability or some sort of conditional random match probability. But this is the basic idea of the second stage of the two-stage approach. And so once you have completed both stages, then there's some decisions that you can make. So if you fail to exclude or reject in stage one, and you have what's sort of considered a small random match probability in stage two, then this would be very strong evidence in support of the prosecution proposition. However, if you failed to reject and you had a very large random match probability, this might be considered to be only weak evidence supporting the prosecution proposition. And then just all out rejecting or having an exclusion in stage one would be strong evidence supporting the defense proposition. Now, this second stage, like I said, is really a little bit wishy-washy because we don't really have a defined threshold on what is a small or a large random match probability. So that's something that would need to be defined if you were to use this two-stage approach. You need to figure out what that threshold is. Maybe you could look at things sort of along the frequentist idea of controlling for your type 1 and type 2 errors, let's say. But one thing to note here is that this two-stage approach does not directly give you a value or a weight of evidence. So this is not something that Good would call a value of evidence or a weight of evidence approach. It just gives you a way to make a decision. And so here are some sort of common interpretations of things that I've sort of seen lately that I think could be interpretations that come from the two-stage approach. So an interpretation of stage one might be something like the glass fragments from the suspect in the crime scene are chemically indistinguishable. And this is something that is sort of recommended for how you would interpret that first stage of the two-stage approach from the ASTM standard. Interestingly, I believe that this would be an acceptable or consistent interpretation with the uniform language of testimony and reporting that the DOJ has recently put out for glass. So that would fit within that. Another type of interpretation you might hear is maybe the suspect's firearm couldn't be excluded as the weapon that fired the bullet. Again, this would be a stage one type interpretation. And again, I think this is something that would be accepted as part of the uniform language of testimony and reporting. I'm not sure about the second one or the third one, because I think the uniform language for testimony and reporting of DNA talks about likelihood ratios, where this one is talking about a random match. But anyway, some sort of interpretation that might come out of the second stage here is the probability of obtaining a matching DNA profile is 1 in a million if the specimen came from some unknown person that's unrelated to the suspect, for example. So here are some sort of typical things that we hear a lot that I would say are interpretations more in line with the two-stage approach than with a value of evidence approach. Okay, so after we sort of dabbled around with the two-stage approach, we're getting closer and closer towards methods that are using Bayesian statistics. So this gentleman, Kaplan, talked about using Bayesian decision theory mostly at the offense level in court. And then in 1970, there was this nice paper by Finkelstein and Fairley, and they talk about this sort of famous case, the People versus Collins. And so there were this interracial couple that was accused of a robbery, I believe. And so what they did is they multiplied the probabilities together of observing this same interracial couple with, a blonde-haired lady with a black guy. I think he had a mustache maybe. And so they multiplied these probabilities together when obviously some of these things were not independent. So they mostly talked about this sort of example at the offense and activity level, and they basically said, instead of doing this mistake of multiplying the probabilities, you can use Bayesian decision theory to get there at a better way. And then I read in this dissertation by Kwan that there was a group of people who explored the use of Bayesian classification rules at the source level. So we're getting closer to the source level stuff that we typically deal with. Of course, Bayes classification rules are not necessarily Bayesian, but we're getting there. And then finally, we get to what I like to say is all hail Saint Lindley for forensic science. So this wonderful gentleman came up with a really formalized and very readable way of computing the Bayes factor for forensic identification of source problems. So we have this guy to thank for the type of work that we do today. And basically what he said is if you have a parametric form that you can think of for your probabilities, then you can come up with the Bayes factor using this ratio of these two marginal likelihoods. And so here that F portion is the likelihood of observing your evidence under the two different models. Here we're talking about the model for the prosecution and the model for the defense. And then here the integration part, that means we have to include the prior information as well. So that's what those funky capital Pi's are for. I want to mention that these priors are very different than the priors for the hypotheses. So when you're doing a Bayesian decision framework, you need to make sure to keep your priors for your parameters separate from your priors for your hypotheses and make sure that you know which one's which. And here I've used, P's and D's to note prosecution and defense, but a lot of times that theta P and theta D, they'll be equal, they'll be the same theta. So a lot of times we'll drop the P's and D's there because they can be denoted by the same vector. And so what we have right now is, I think, something that's a bit of a confusion. So after Lindley came out with this paper, there was a commentary paper on it. And in this paper, the approach that he used was referred to as a likelihood ratio approach because it used likelihood functions and it was in some sort of ratio. And then later on with this my loving glass problem, Evatt followed up his two-stage approach with a Bayesian approach, but then referred to his application of that approach as a likelihood ratio, when in fact both of them are Bayes factors. And then the DNA craze begins, and there's all sorts of publications, and everybody says that they're using a likelihood ratio approach. And to be fair, in the case of DNA, we have this level of scientific knowledge that allows us to basically get rid of all the uncertainty that would be associated with computing a Bayes factor. So in the case of DNA, a lot of times the Bayes factor and the likelihood ratio are completely equivalent. And so we started calling everything likelihood ratio, and we basically dropped the term Bayes factor, or sometimes we would call it a value of evidence. But the word Bayes factor doesn't really appear very much anymore in the forensics literature, which I think is a shame. I also want to note that there was a webinar a couple of years ago at NIST where somebody asked Professor Evatt particularly about this problem, why he called it a likelihood ratio, and he said that he very much regretted calling it that and hoped that we would call it a Bayes factor. So if Professor Evatt says it's okay, I think it's all right to call it a Bayes factor now. So essentially what happens in the case of DNA is that any uncertainty about the parameters that we see here for the likelihood ratio essentially goes away. There's not much uncertainty, and these parameter values are essentially known. So if you have parameter values that are essentially known, you have what we call this true likelihood ratio. So that means you know specifically how to model the likelihood of your evidence under the two competing models, and you specifically know the values of the parameters as well. So this gives you directly one number for the true likelihood ratio. In the case that it's not DNA, we don't typically know what those values are. So if we're not working with something like DNA, we typically look at just the likelihood ratio function, and this is just a function of your unknown parameter values, and typically we try to estimate them in some way and figure out what they are. So we can see here that the likelihood ratio and the Bayes factor share some commonalities, but the likelihood ratio only deals with the evidence here for unknown source. That's why I have the subscript U, because anything that has a known source is going to cancel out of this formula. Whereas before, if you have some sort of uncertainty and you're doing a Bayes factor calculation, you need to deal with your entire set of evidence, where here you only have to deal with your unknown evidence. So some sort of interesting things came out of this. So there are some papers that talk about ways to sort of avoid some of these common pitfalls when you're interpreting forensic evidence. So in 1982, there was this nice paper by Schaefer that talks about Lindley's paradox. So Lindley's paradox is where you have two different methods that are aimed at answering the same question, but they give you opposing answers. So whatever values you get for the two different methods are going to point in opposite directions. So that's something that we need to be careful of when we're interpreting evidence to make sure we don't fall into Lindley's paradox. Because that's something that could really wreak havoc on a court, is if two different experts present evidence that point in opposite directions, then we're not being very helpful there. There's this other paper by Good from 1985 that talks about the consequences of using bad terminology. So he basically said if only one faction is using that type of terminology, and we're not collaborating and deciding what type of terminology we're using, then we can really have sort of far-reaching effects for just picking the wrong words. So good basically says that the right words matter. Some of the other common pitfalls of interpreting evidence are falling into this idea of what's called the prosecutor's fallacy. So that's like taking an interpretation of the value of evidence and treating it as if it was an interpretation of your posterior odds, or what you were actually interested in for the courts is the probability of the two competing propositions after you've observed the evidence. So that's a good thing to avoid when we're thinking about interpretation. And then another paper by Philip David talks about the island problem, and this kind of pulls together all sorts of common things that could go wrong when you're thinking about forensic evidence, kind of in this cool little isolated island situation. So that's another thing that has led us up to the point that we are at today. Okay, so we still don't know exactly how the hell we're actually going to compute this value of evidence, or the Bayes factor, and there was a lot of research, particularly in statistics, about how to actually do this. A lot of it happened, I think, in the 90s. So we can talk about, just very briefly, estimating parameters, types of asymptotic approximations you might use, maybe different Markov chain Monte Carlo methods, some more Bayesian computations, non-parametric approaches, and many, 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 many other things that you could do to compute values of evidence. So if you're particularly looking at a likelihood ratio function and you need to estimate the values of those uncertain parameters, there are a variety of things you can do. You can use maximum likelihood, you can use method of moments. If you want to have a more Bayesian flair, you can look at things like taking the posterior mode or the posterior mean. So you can do all of these different types of things. Not all of these methods are created equal, but one thing that you need to particularly be interested in here is what collection of data should you use to actually find this estimate from. So do you use the entire collection of data? Do you use just the unknown source evidence? Do you throw the unknown source evidence in with some stuff that you know? And so there's a really nice paper by Philip David that kind of talks about the different things that you could do here that I think is fun. So if you have a likelihood ratio, you need to estimate some things. Here are some ways that you could do that. Another thing that we can do is just to use an asymptotic approximation of the integrals or probabilities that make up the Bayes factor. So you could do something like a traditional Laplace's approximation, and this uses the maximum a posteriori estimates. Or you can do some sort of variation of that, and since the map estimates are not readily available, maybe you can use MLEs instead, because those are pretty readily available from most common softwares that we use. Or if you want to look at the weight of evidence instead of the value of evidence, you can use something like a BIC, which is related to the Schwartz criterion. So you can use these different types of popular asymptotic approximations to get at the value of evidence. Or you can use things like Markov chain Monte Carlo methods. So different types of Monte Carlo integration was essentially the focus of my master's work here. So you can do things like a straight arithmetic mean, or you can do a harmonic mean, or many other important sampling type things. You can use Hamiltonian Monte Carlo, or a variety of other MCMC methods to compute these things. So I have not particularly looked into the last four, but I think they might be interesting things to look at in the future, since they're more popular methods than Monte Carlo integration is now. Some other things that you can do is, if you have a particularly difficult likelihood function to work with, you can do approximate Bayesian computation for model selection. And then I think it would be fun to look into partial Bayes factors, or intrinsic Bayes factors, or fractional Bayes factors, something like that. So I've looked at these a little bit. I know that they are probably applicable to forensic science situations. As far as the other things like variational Bayes, inla, or empirical likelihood, I'm not sure that those are applicable, but I've been hearing a lot about them at like ISBA conferences and stuff. So this might be some interesting things that we might want to look at in the future as well if we are trying to compute Bayes factors. There are tons and tons of non-parametric approaches. I am in no way an expert on this, but there are a couple of kernel density estimation techniques in a couple of papers by Aitken that I particularly thought were interesting, so you might take a look at those. And just sort of finally, as a overall thing about computational methods, like I said, not all methods are created equally. Some methods I'm not even sure are directly applicable to forensics. If they are, you might have to jump through a couple of hoops. A lot of these methods are really highly sensitive to the choice of prior distribution. So that could be particularly problematic in court situations, for example. Some of the methods are really highly variable due to the simulation that's necessary. So for instance, the harmonic mean Monte Carlo integration just gives you wildly varying results. And some methods are really computationally inefficient, and this could take just a really, really long time to actually compute a value of evidence, and many other things that we should be paying attention to. I'm sure you could go on and on about different drawbacks of each of these different methods. Excuse me. So because these Bayes factors are just so dang hard to calculate and compute a value for, particularly in the case of some of these types of evidence that I've listed here, a lot of people have sort of moved away from them and have started looking at things called score-based likelihood ratios. And so score-based likelihood ratios are very popular lately for things like voice or speaker recognition, fingerprints, handwriting, shoe prints, bullets, glass, and many other things. There's just tons of literature out there about things that are happening with these methods. And so the basic idea here is that a score is some sort of measure of the similarity or dissimilarity between two different items of interest. And the idea is that it's much easier to model the distribution of these univariate scores than it is to actually figure out what the likelihood would look like for some very multi-dimensional, complicated handwriting evidence, for example. And so what we do is we basically get a distribution of the scores under HP, or the numerator, and a distribution of these scores under the denominator. And then we look at the ratio of the two heights corresponding to that particular value of the score. Here we call it delta. And so that's the basic idea of score-based likelihood ratios. Some sort of criticisms that have come along about forensics and evidence interpretation in general. In 2009, we had the National, let's see, what does NRC stand for? I'm drawing a blank. Research Council, thank you. It was there somewhere. So we had the NRC report, and they basically said we need more research, we need more publishing, and I think we're doing pretty good on that. They called for improved methods of reporting forensic conclusions, and so we're getting there with things like verbal skills for likelihood ratios, and this is something that comes up over and over again. How do we report these conclusions in the proper way? And I don't think it's going away anytime soon. They also called for things like error rate studies, like black box, white box. Same with PCAST. They really want to have these black box, white box studies. And then in around 2015, we found out that, well, score-based likelihood ratios are very useful. We can't actually call them a value of evidence because they're not logical and they're not coherent. So there are some issues with score-based likelihood ratios actually being called values of evidence. So you can't use them in place of a Bayes factor to say update your prior odds to arrive at your posterior odds, but they're still very useful. And so right now what we're dealing with are some of these issues that have been coming up from the PCAST report. So are the methods for impression and pattern evidence reliable, or are they valid? And so I believe that's about all I have to say for you guys. That's my conclusion for part 1. There's plenty of information and work out there, so please come back for part 2. This is a complicated and collaborative effort that we're working on. I think it's very cool that the Bayes factor has been defined or as a value of evidence for over 50 years, but yet there's still confusion between the Bayes factor and likelihood ratio. So if you want some ideas about how to distinguish the two, please come back for part 2. And I have a giant list of references for this that I didn't want to put on slides, so probably post them with the presentation, or you're welcome to email me and I can send them out to you. So thank you for joining, and I will be happy to answer any questions.
Sure. So my first question kind of resides really early in the presentation when you were first.
Green.
Use this one.
Green. Oh, okay. What is this? Are these like different?
It's micro.
Oh, okay. Okay. I thought this was a clicker for a second. Okay. So my first question involves really early in the presentation when you were first introducing HP and HD, and just because I still have a very, not weak, but I guess Swiss cheesy understanding of what a Bayesian model is. Just wanted to, I guess, clarify or affirm what I think what's going on.
Sure.
So would a fair, I guess, example of HP and HD, are those like things in the background that are going to be impacting our end result?
That would be like what I is. So I are these sort of background things that are impacting our results, but what the propositions are basically a statement about kind of what you're trying to show. So something like HP and HD could be like, you know, the glass fragments that were found at the crime scene, or that were found on the suspect came from the crime scene, and HD would be that they don't come from the same place.
Okay,
so it would be a statement about, like it can be at various different levels, but if you're looking at source level, it's a statement about where your evidence has originated.
Okay. Okay, so that makes a lot more sense. So I'd probably tie in I more with the definition of a Bayesian model, which to my understanding is something about a school of thought where background knowns impact your end result.
So yeah, so there's a couple of pieces here. So the background known stuff can also be incorporated into that prior odds.
Okay.
But we can definitely talk more about it.
Sure.
So let's see. Oh yay, I have a reference. Okay, can everybody see those questions or do I need to repeat them?
Everyone should be able to read them in the chat.
Okay. So thank you. And I will take a look at that reference. And
Nice.
oh, sure, Jeff. I will definitely get in touch with you.
Nice.
Any other questions? I like lots of questions, so.
Anyone else out there with a question?
Are the I have a question as well.
Okay.
When you're talking about the hierarchy, of hypotheses, was that descending or ascending, or was it hierarchical at all? It was one, I guess.
So like offense level would be the most serious.
Okay.
And then going down to subsource or source level can be less serious. So offense level they have to have things like motive for committing the crime, and they have to have actually done the actual thing. So like with the example with Mrs. X murdering her husband, the most serious is that the offense, she actually murdered him. The less serious is maybe she shot in self-defense, that would be activity level, and then going down and down. So I would say like the offense is the most serious, going down to subsource is less serious.
Okay, that makes sense.
Oh, I'm not sure that I can tackle that in a couple of minutes.
Is this something you're going to talk about next time?
This is something I very well can talk about next time. That's fine.
Oh.
Hmm.
See,
I assume that's Chris. Sorry, Chris.
working on it, Chris. Sorry about that.
So Danica, can you read the question that came from UCI and then restate that you're going to talk about that next time?
I pasted it back in the
Oh,
chat.
you did.
Oh, okay.
Awesome, thank you.
Okay. I honestly don't know if I have ever looked at specifically how somebody like O'Hagan defines subjective probability. So I'm not sure that I can comment on that. That's something I'll have to go back and look at.
We'll see what it said.
I'm not sure. I wonder how I'm interested now about how he defines subjective probability.
Other questions or comments?
Is this a presentation on our GitHub?
Um,
Oh, is this a presentation on our GitHub? I'm really interested in the picture that correlated numbers to, I guess, more formal.
I think
definitions.
so. The presentation, like all of them, are going to be posted in forensicstats.org. So everything goes in resources, right? Go to resources and scroll down, and resources for researchers.
Yeah.
Yeah. Oh, and at the Education Center, sorry. I think we're done. So don't forget, everybody, thank you for the comments and thank you for joining us today. And part 2, that promises to be fabulous. February 4, see you then.
Thank you.
Bye-bye, have a good